Last week, we mainly discussed the limitations we have with the quadratic element. So we discussed variation of situation where you cannot use the quadratic element unless you think about how you use that. Now I'm going to start this week by asking you to solve this example using a quadratic element, and we are going to discuss the example afterwards. So this is example number 12 in the unit number 1. So please start recording, and if you have questions, you can ask them. Obviously, the midpoint, the central points in the stiffness matrix we developed, in the elements we developed so far, the stiffness matrix was developed for a situation where the midpoint or the central point is right at the middle of the length. So it is located at this point here, right? So this is how we develop the stiffness matrix. If you go back and see the shape functions, you will see that the second shape functions were developed for a situation where the midpoint or the central point is at L/2. Now this one is at L/4. So obviously the stiffness matrix, the shape function would be different, and the stiffness matrix would also be different. All the shape functions would change, and this would result into the change or at some changes in the B matrix, and this will result into some changes into the stiffness matrix. So the stiffness matrix would look different. Okay, so we agree on that. But now we need to think about something else. There's some other problem in there. What is that? Here in this example, we have a concentrated load, all right? So we don't have a concentrated load, so we don't have a distributed load. So the equivalent load vector, obviously, if this is a distributed load, then we would have an equivalent load vector. And if you remember, I'll probably just show you quickly the equivalent load vector we discussed at the beginning of the lecture last week. Example number 8, yes. So you'll see that the equivalent load vector would be this one. So it is WL/6, 4WL/6, and WL/6. And this F2 would be located right at the center, right? So it would be possible to use the stiffness matrix. And by definition, this type of load is developed for a situation where we have the point is in the center. Originally, you don't have, if you look into this problem here, you don't have any limitation on where you want to put your central point, right? You can put it in the middle, but you can put it here, or you can put it here. It's completely up to you. There's no restriction on you on where to put the midpoint. You develop the stiffness matrix for a scenario where the midpoint is in the center. So this is why you calculated the load vector so that F2 is 4W/6 and is at the center. Okay. Now, in this case, this is different. In this case, you have a concentrated load, and the concentrated load is by definition at this point here. I'm going to use my pen to put some marking on there. So by definition, this concentrated load is located at this node here. So you cannot control that. You don't have control over this. You are not making assumptions and assuming that this distributed load is located to or lumped into nodes. What you have here is a load by definition located at 1/4 of the length. Okay? You see that? However, you are right on this, but so if you want, the limitation or the problem we have is also related to the node, to the load. So in the sense, you are right, but it's not the exact problem you mentioned. What is the problem here? So you're suggesting we have one element, will go between L4 and L4, yes. And then the midpoint will be the end of the first element. So this is your first element going here, and then you have a second element like this. This would be, in this case, it would be possible to use this stiffness matrix there So this would make it possible to use the stiffness matrix. We don't need to develop a stiffness matrix, but there's still one problem in there. And I've probably spent the majority of the last week discussing this very specific problem. So I want you to see that. I don't want to overlook it. If we use one 3-noded element, just like this one here, of course, we are going to have different N1, N2, and N3. This is we mentioned, so we don't know them, how they would look like. As you have all mentioned, it is the case that we cannot use this 3-noded element to solve this problem because this is at L/2 and L/2. This is the stiffness matrix that has been derived for this element, and this is not the case here. If you are going to use one 3-noded element, then this one 3-noded element will be in a situation where the second node is quarter of the length, so it's right here. It's not the mid-length, where we developed the shape functions and the stiffness matrix in the previous case for an element where L/2 and L/2 is at the middle. So in this case, in order to be able to solve this using one 3-noded element, we need to rederive the shape functions. So I'm not going to get into the details of deriving the shape functions because we have done that and it's exactly the same process. So we have the displacement defined as a quadratic function. We have a 3-noded element. It is a quadratic function. So we have A1, A2, A3. In the past, I did AX squared plus BX plus C, which is pretty much the same thing. I hope you see that this is the same. Now, at X equal to 0, you have, I'll probably just write it quickly, A multiplied by 0 plus B multiplied by 0 plus C. And this will be equal to U1. So this is at X equal to 1. So you have U to be equal to U1. At X equal to L/4, you have U to be U2. And then you have this to be equal to A L/4 squared plus B L/4 plus C. And finally, you have L. So this is U equal to U3. This is the last point. And this is equal to A multiplied by L squared plus B multiplied by L plus C. You need to solve. So you need to solve this system of equations. You have 3 equations with 3 unknowns. From the first equation, you immediately get U1 to be equal to A1. And then you have 2 equations left. So you replace this one with U1, you replace this one with U1, and you have 2 equations with 2 unknowns. So this is the first and this is the second unknown. So these are the unknowns you are solving for. All right, you solve that, you get the value of A1, A2, and A3. You put these values back into this equation. So you replace A1, A2, and A3 with whatever value you have for them from here. And you do that and you rearrange. So first you take everything to do with U1 first, and then you put everything to do with U2 second. I'll probably just put it in a square. And then finally you have everything to do with U3 third. I just put it in a triangle. You just rearrange for that and you'll have your shape functions. You'll see that this first shape function is here and here and here. So these are the shape functions. You need to go through the entire process one more time. You need to define the B matrix. The B matrix is the derivative of the shape functions with respect to X. So you derive these with respect to X, and then you get that. And then you need to use the B matrix, transpose multiplied with the B matrix, integrated over the volume. Now this will give you A, and so on and so on. And then you can get the stiffness matrix. Now, if you look into the stiffness matrix you get in this case, you'll see that the stiffness matrix here is quite different. I mean, see, this is 19/3. In the past, you had 7/3. So this is quite different. -8/3. This is 64/9 now. So it's very different. And if you look into the shape functions as well, you see that the shape functions are also very different. So the shape functions, we had them in the past. I hope I have them somewhere here. This is the B matrix. This is still the B matrix. Yeah, we have it here. So this is N1, So you see that n1 is 1 minus 3x over L, 2x squared over L squared. So this was the n1, whereas the n1 now is quite different. It's 1 5x over L, 4x squared over L squared. So this is quite a different shape functions. Now we have the stiffness matrix. We can use the stiffness matrix to solve the problem, right? This is the new stiffness matrix. You solve it. You solve the problem using the new stiffness matrix. You get delta 2 and delta 3 to be these numbers. Now, like Jacob said, if you solve the problem and you get these displacements, you are going to make some error in the displacement. I mean, if you solve the problem exactly, you see that these ones are not quite correct. I'll probably just put an X next to them. So there'll be an error in this displacement. If you compare them to the exact displacement, why is that? You did the derivation for the shape function. You did the derivation for the stiffness matrix, but you're still getting not correct results. Why is that? I mean, it is a good approximation, so the actual number is not going to be very different, but still is going to be some difference in there. So why is that? Can you tell me? I've spent the chunk of last week discussing the situation where we have a concentrated load, right? I mean, we had this example where we have one concentrated load at midpoint, and we used the stiffness matrix of the three-noded element, this one, to solve the problem, and we still get some wrong displacement at the midpoint, right? Remember that? Now, we had this because it is not the displacement. I mean, the displacements are going to be different. It is because of the stresses and the strains. So the stress and the strain is going to be constant here and constant here, whereas the one element shape function will try to interpolate the stresses as a linear variation. Now, it's going to try to match a line to this point, this point, this point, and this point. So this is a step-like function, right? And you are trying to draw a line that can pass through these 4 points. Now, the finite element is not going to be able to do that. It's going to try and minimize the difference. So basically, what the finite element is going to do is trying to find the minimum displacement for all these points from the line. So it's going to find what we call in math the best fit for this. All right. Now, the best fit is not good enough because you're trying to do a line to interpolate a step function. So it's not going to work. All right. So this is what we discussed last week. And I came back to this point because I think it's quite important. And this is what I has been hitting at from the start of the lecture today. All right. In this case, see, if you come to this example, you see that this is pretty much the same situation. You have a concentrated force at or inside the element itself. So this is going to result into a jump in the stress. If you are going to draw the stress in this case, you see that this is the cantilever. The stress is going to be like this, and then it's going to drop and then do like this. It's not going to be zero. It's going to be constant. And what you can do with this new element you derived, with this new element here, if you use that, again, is going to face the same problem and is going to try and find a line that is going to fit through these points here. So a line that is going to fit through these points is going to look like this and is not going to match or not going to go through any of them. It's just going to avoid all of them, but it's going to try and minimize the distance between the line and the points. It's going to be better to use linear, but you can still solve it accurately with the quadratic element and use two elements. I would say we need to have the third point here, and then you have the second element here to cover the remaining of the problem. So you have one element going for 1/4 of the length and the second element going for 3/4 of the length. So the thing is, if you have the point to move to probably 1/5 of the length, I mean, the second point, probably the distributed or the concentrated load is at 1/5 of L, or if it is 3/7 from L. I mean, to think about how many possibilities you have, and then you will find that this is a huge number of possibilities, and you need to rederive the stiffness matrix, the shape functions, and it's a very lengthy process. I mean, it will make the finite element method completely worthless. And this is the case in 1D, but I'm going to show you the situation in 3D. Sorry, in 2D. I mean, just let us do it in 2D. Now, in the 2D case, you are going to derive the stiffness matrix for your element. Let us assume that this is a triangular element, and you are going to derive the stiffness, the shape functions, and the stiffness matrix for that. And then you are going to use this triangular element to mesh the problem. So if the problem is very uniform, so you have, for example, a square, then you can use this triangle. And yeah, I mean, with some twist, probably, you can use exactly the same triangle. I mean, if this length is 0.1, you need to fit that in there, so 0.1, and assume that this is a unit square. So this is 1, and this is 1. So you can fit 9 of them in here, 10 of them, you can fit them in here, and then you would solve the problem, all right? So it would work. However, in the vast majority of the cases, you don't have uniform geometries and you don't have regular geometries. You are going to have complex geometries. For example, you are going to try and solve a problem like this. And you want to identify the stresses at these points, for example, or you're trying probably to solve a problem where you are looking into a biological geometry. And then in this case, it's not going to be anything uniform. It's going to be anything but uniform. So in this case, you are going to use a variation of triangles. And I guarantee you, it is very unlikely that you will find 2 triangles that would look the same. So you will always find different triangles. So if we follow the same strategy we just did in this case, if we follow exactly the same strategy, then in this case, you are going to need to derive the shape functions and the stiffness matrix for this element, the shape functions and the stiffness matrix for this one, and for this one. And if you have 1 million elements in your mesh, you're going to need to do this 1 million times. And this is completely meaningless. And the finite element method is meant to be simplifying things, not complicating them. So if you do that, you'll be really complicating the problem, not solving it in an easy way. So the alternative is to find some way where you derive the stiffness matrix and the shape functions for this single element. Let us assume that this is X and this is Y. And then the length is 1 here and 1 here. And then you find some way to map these triangles into this element every single time. So you find some way to transfer these triangles. I mean, this is a process we call mapping in the finite element. So you map all these elements back into this single one. And you can then build the stiffness matrix for each one of them using this single element you have derived at the beginning. Now, the process itself, or the mapping process itself, is not easy, is slightly complex, but I'm going to try to simplify it as much as I can. All right. So I'm going to try and simplify it by deriving it for a 2-noded element. So I'm going to show you how it works, this process for the 2-noded elements. But this process for a 2-noded element would make absolutely no sense because you can easily map things. I mean, think about elements of different length, but all of them are 2-noded. So you have one element here and one element here and one element here, and you want to map them, you can simply just multiply them by a scaling factor if you want. So if this is 1, and this is, I don't know, this is L over 5, and this one here is L over 2, and this one here is L over, this is L over 20, and this is L over, I don't know, 3, for example. So you can just multiply them by the scaling factor, and you can map them into this new mesh. Right? The process itself is so easy for 2-noded elements. However, I'm going to derive it for the 2-noded element using the full length of procedure so that you can understand it for the 2-noded element. And then we are going to move to 3-noded element, and then I'm going to explain it for 2-dimensional problems. All right? So what I'm going to do today, the bulk of the material I'm going to discuss today, is just how to map these general elements into a reference element. Okay? So this is basically what I'm going to do today.